This is a presentation to introduce you to the units and techniques that scientists use to make measurements. There are 3 countries in the world that don't use the metric system. There's Liberia in Africa, Myanmar in Asia, and the US in North America. The rest of the world uses a sane, rational system, while we use the outdated imperial system. Except for scientists, we use the metric system. We will use the following units when we take measurements in this class. The beauty of the metric system is that you can use the same base unit and make it very small or very large by adding a prefix to it. For length, the base unit is the meter, which has the abbreviation of M. For volume, which is actually a derived unit, length cubed. But in chemistry, we measure volume quite often, and the base unit we use is the liter. The abbreviation for this is the capital L. We use the capital L to keep it from being confused with the number 1. For mass, we use the gram with the abbreviation G. For temperature, we use either the Celsius temperature scale or Kelvin. And for time, we use the same unit as you are used to, seconds. We'll talk more about these prefixes for these units in another video. We need to make a distinction between measurements and exact numbers. Measurements have a unit and give an indication of the type of instrument used to make them. I'll explain this more in a moment. There's always some uncertainty in a measurement. On the other hand, exact numbers have no uncertainty. Exact numbers are those that come from counting objects. Here we have exactly 3 planes, and not 2.99 or 3.01. The 3 is exact. Another type of exact number arises from definitions. In the imperial measurement system, 1 foot equals 12 inches by definition. There are exactly 60 seconds and 1 minute. Those numbers are exact and have no uncertainty. All measurements involve some uncertainty. So when we make a measurement, we need to include all of the known numbers. These can be found as markings on the instrument we use. We also need to include an estimated digit, which can be found between the lines on the device. This is easier to show you than it is to explain. Let's say that we need to measure this piece of wood. If we use the ruler on the top, we can say that the wood is between 3 and 4 centimeters long. So we start off our measurement with a 3. Then we can estimate how far the wood lies between 3 and 4. And this will be our estimate. I think that this is close to halfway between the 3 and the 4. So I would record this measurement as 3.5 centimeters. You might think it's closer to 3.6 centimeters, but it doesn't really matter because by reporting the length either as 3.5 or 3.6, we are telling other scientists that the last digit is an estimate. By using the ruler on the bottom, we can have more confidence in our measurement. We can now see that the wood is between 3.5 and 3.6 centimeters long. And if we zoom in, when I look at this, I think it is about 7/10 of the way between 3.5 and 3.6. So I would report my measurement as 3.57 centimeters. So even though we measured the exact same stick, the measurements that we record differ based on which ruler we used. So what happens when the wood lies directly on a line? Well, in the top ruler, we would say that we know it is between 4 and 5 or 3 and 4. So 4 is our first digit, and that's our known digit. But then we have to estimate how far the wood is between 4 and 5. In this case, we would say it is 0.1 away from the 4, and our reading is reported as 4.0 centimeters. For the second ruler, we know that the wood measures between 4.0 and 4.1 due to the markings on the ruler. Our known digits are 4.0, and our estimate is that it's right on that 4.0 line. So it is 0.1 away, So our measurement would be recorded as 4.00 centimeters. Students often have trouble with this concept. Remember that every measurement must include an estimated digit. You're going to look at the markings on the instrument. The top ruler has markings every 1 centimeter. So our estimate is going to be in the tenths place. The bottom ruler has markings every 10th of a centimeter. So our estimated digit will be in the hundredths place. Chemists work with solutions often, so making good measurements of volume is important. We usually use glass tubes or glass instruments that are tall and thin. When water is placed in thin tubes, it forms a meniscus. And this is the concave surface that is shown here. Depending on the width of the tube, this could be quite deep or barely noticeable. But however it appears, we always use the very bottom of it to take our measurements. In our instrument on the left here, we can see that there is a major marking every 100 milliliters and a minor marking every 10 milliliters. We can see that the bottom of the meniscus is between 180 and 190 milliliters, and we can estimate that it is about 2/10 of the way between 180 and 190. Therefore, our measurement would be reported as 182 milliliters. You might see it as 183 milliliters, but since our last digit is an estimate, that isn't quite so important. In the measuring device on the right, there are major markings every 1 milliliter and minor markings every 10th of a milliliter. We can see that the bottom of the meniscus is between the 22 and the 23. Should note that the scale is upside down. Some instruments are used this way, and some of those that we will use in the lab are used this way. So we can see the meniscus is between 22.7 milliliters and 22.8 milliliters. I think it looks really close, but not quite at 22.8. So I would report my measurement as 22.79 milliliters. Instruments with digital readouts do the estimating for you. This balance is reporting the mass of these washers as 20.813 grams. The estimated digit is the 3 in this case. We'll talk more about significant digits in other places, but since these are dependent on measurements, I want to introduce them here. Measurements should signify the type of instrument used to make them. Hopefully you now understand this based on the length and volume measurements we've made so far. But let's look at a special case. Let's say that we want to measure a liquid. We pour it into the first device here. It's called a graduated cylinder. It has major markings every 100 milliliters and minor ones every 10 milliliters. The volume could be recorded as 300 milliliters, where our estimated digit is the last zero, right? If we have marking every 10, then our estimate is going to be in the ones place. But, so we would report 300 milliliters. But if we had used the graduated cylinder in the center, we'd be tempted to report 300 milliliters as our measurement, but that would be wrong since our estimate is in the tens place. We still have to convey that there was around 300 milliliters of liquid, so we can't report 30 as our measurement. We would have to report our answer in scientific notation instead. We would say it was 3.0 times 10 to the second power milliliters. In the last graduated cylinder, we only have a marking every 1,000 milliliters, so our estimated digit is the 3. We have to convey this, so we would have to report our answer as 3 times 10 to the second power. As I said, we'll talk more about significant figures in a future lesson,